chapter work energy and power exercise. First question, you have to calculate the sign of work done, whether it is positive work or a negative work. First case, work done by a man in lifting a bucket out of well. The man applies force upward to lift the bucket, and the bucket moves in the same direction. As force and displacements are in the same direction, the work done is positive. Then second case, work done by gravitational force in this case. When bucket moves upward, gravitational force is downward as force and work are in the opposite direction. Work done by gravitational force is negative. Then third case, work done by friction on a body on an inclined plane. Always friction is opposite to the motion. Therefore, the work done by friction is negative. Then case D, the work done by an applied force on a body moving on a rough horizontal plane with the uniform velocity. So anyway, you need to apply a force to overcome friction because it is a rough surface, but the object moves in the direction of the force. Therefore, we can say the work done is positive. Then next, work done by the resistive force of air on a vibrating pendulum in bringing to rest. The resistive force means it is something like the opposing force only, air friction we can say. So as it is opposing force, we can say the work done by the force is negative. Okay. Now come to question 2. A body of mass 2 kg initially at rest moves under a force in the horizontal direction, a force of 7 Newton. Okay, so what are the quantities given? Mass is given 2 kg, 2 kg mass. Then the applied force is given 7 Newton, and coefficient of kinetic friction mu k is given as 0.1. Then compute. First case, the work done by the applied force in 10 seconds. Okay, so time is given. So case A we can take. Time is given 10 seconds. 10 seconds. So first what you have to do, you have to find the friction acting on the body. The friction acting on the body, you can calculate Fr is equal to mu mg. Once you get the value of friction, you can calculate the acceleration on the body. A is equal to applied force F minus friction divided by mass. Net force divided by mass will give acceleration. Then when you get the acceleration, you can use the formula S is equal to ut plus half at square. S is equal to ut plus half at square to find the displacement of the body. Okay, again you see the body starts from rest, therefore u is 0 only. Find the value of S. You will get around 125 or 126 like that. Okay. Then once you get the value of S, you can find the value of work, which formula you can use. W is equal to force into displacement. You will get the first answer for case A. Now next, work done by friction, case B. Work done by friction in 10 seconds. How can you calculate work done by friction? Again, directly you can calculate because friction you have already calculated. So friction Fr, that is equal to mu mg into S will give the work done by friction. Then next, work done by net force on the body in 10 seconds. Case C. Work done by net force means, again you can use the same formula, but the difference is that you have to find the net force. Applied force F minus friction Fr. That is the net force. So net force into displacement S will give the work done by net force. So you will get the answer. Please find the answer there. Now, case D. Change in kinetic energy of the body in 10 seconds. For case D, we can apply work energy theorem. That is, work done by net force is equal to change in kinetic energy. Okay, which means the answer which you got in case C will be equal to change in kinetic energy. Work done is equal to change in kinetic energy. That is F minus Fr into S. That is work done by net force is equal to change in kinetic energy delta K by applying work energy theorem. Okay, that means the answer to part C and D is same. Okay, that's about question 2. Now, question 3 graphs we have already discussed in the class. Now come to question 4. Question 4, one graph is also given there. Okay, Vx is equal to potential energy Vx is equal to kx square by 2. The formula already you have derived. Potential energy Vx is equal to kx square by 2. Now, value of k is given 0.5 Newton per meter. That's a spring constant, like that you can take. Then what you have to find? Show that the particle of total energy 1 joule. Total energy is given. Total energy 1 joule. 1 joule. Moving under this potential means potential given by this equation V is equal to k square by 2 must turn back when it reaches x is equal to plus or minus 2 meter. You have to note that turn back. So what's the meaning turns back? You take the case of a pendulum. So it's a oscillating body like a spring or pendulum, whatever be. Okay, either you can consider a spring or you can consider a pendulum, whatever be. See here, this pendulum is oscillating. And when does it turn back? It goes to the extreme position. After reaching extreme position, it is momentarily at rest. Then it turns back. So any oscillating body that turns back means the body is at extreme position. Okay, so that is our conclusion. The body is at the extreme position in oscillation. Now, at the extreme position, think about the energy. At the extreme position, you can see kinetic energy equal to 0. Therefore, total energy is equal to potential energy. Total energy is equal to potential energy. I am going to take that concept. Total energy is equal to potential energy. Then you will get potential energy k x square by 2 is equal to total energy is given in the question, that is 1 joule. Now substitute the values of k and okay, only the value of k you can substitute there. So when you substitute the value of k, you will get x square is equal to 4, or take the square root of the equation, x is equal to plus or minus 2 meter. That means when the displacement is plus or minus 2 meter, the body turns back. That only you are asked to prove. The body will turn back when the displacement is equal to, displacement x is equal to plus or minus 2 meter. Okay. So that's about question 4. Now next, question 5. Okay. Rocket propulsion. At whose expense is the heat energy required for burning obtained? So when the rocket is in flight, burns up due to friction. Now at whose expense is the heat energy required for burning obtained? That means what is the source of that heat energy? You know, when you do the work against friction, heat will be produced. You know, even when you rub your palm, heat is produced. What is the reason? You are doing work against friction. Okay. So there, who is doing the work? You are doing the work. Because of your work, heat energy is produced by friction. You can take the same concept here also. Who is doing the work here? The rocket is doing the work to overcome air friction in the atmosphere. So, rocket is doing the work. The work done by the rocket is converted into heat energy due to friction. Therefore, the answer is rocket. Now, part B. A comets move around sun. Okay. Now, the gravitational force on the comet due to the sun is not normal to the comet's velocity in general. Okay. Yet the work done by gravitational force over every complete orbit, that you have to see, complete orbit is 0. Why? So what you have to understand what is the significance of this second sentence given there. Okay, velocity is not normal. If it is circular orbit, what is the situation? When you assume a circular orbit, then we can say here centripetal force is acting towards the center of the circular path and velocity is tangential, and this angle is 90° and work done is 0. And we just claim work done by centripetal force is 0. Finished. But here the question says that this orbit is not a circular orbit, it's an elliptical orbit. As it is elliptical orbit, many times you can see the centripetal force and velocity, tangential velocity, are not normal. That is what given in the question. Still the work done is 0. What is the reason? So here, I have to change the concept. You have to take gravitational force as a conservative force. Gravitational force is conservative. We have discussed in details. Properties also we have discussed. Gravitational force is a conservative force. Being a conservative force, you know, what is the work done to move an object in a closed path in a conservative force field? Work done is equal to 0. So that is why it is given in the question over a very complete orbit. So what is your answer? The work done by conservative force to move an object or a closed path is 0. That is the reason. That means one of the properties of conservative forces you have studied. Okay, come to the next question. An artificial satellite. Again, satellite. Okay. Why does its speed increase progressively as it comes closer and closer to Earth? When the satellite approaches close to Earth, its speed increases. What is the reason? In different ways, we can give the answer. Okay. One of the method we can say you have studied again gravitational force is conservative. For conservative force, total energy equal to constant. Total energy is constant. Total mechanical energy. Okay, total mechanical energy is constant in conservative force field. As total mechanical energy is constant, we can say delta K plus delta V. Delta K plus delta V. We have calculated in the properties of conservative force. Change in kinetic energy and change in potential energy. But total energy is constant. In such a situation, what happens? When the height decreases, what happens? Potential energy decreases. But you know, total energy is constant. So whatever decrease in potential energy, what happens? Becomes increase in kinetic energy. So when the satellite approaches close to the Earth, height decreases, potential energy decreases, so kinetic energy increases. And kinetic energy formula, you know, half mv square. So kinetic energy increases means which quantity increases? You have kinetic energy is half mv square. When kinetic energy increases, the speed v increases. So that is the reason. That's a simple explanation for the part C. Now, next, part D. Okay. A man walks 2 meters carrying a mass of 15 kilogram on his hands. Diagram is given there. He walks the same distance pulling the rope behind him. The rope goes over a pulley and the mass of 15 kilogram hangs at its other edge. In which case is the work done greater? This is a diagram given here. Two cases. Look at the diagram. Case 1 and case 2. Look at there in both the cases, the man carries the load and he walks with the same speed in both the cases. Therefore, we can say as he is in motion, there is a kinetic energy. So, kinetic energy in both the cases are equal. Why equal? Because he is moving with the same speed, carrying the load. In both the cases, he is only carrying the load. Okay. Now look at the second case. Second case, he is moving with the load. At the same time, this object is moving upwards. That means the object is acquiring potential energy. But in the first case, you cannot see any change in potential energy. Therefore, you see the case. In first case, the man is doing work which is just converted into kinetic energy. But in second case, man is having the same kinetic energy. At the same time, he has to do the work to increase the potential energy of the object also. That means kinetic energy as well as potential energy. Therefore, in which case he has to do more work. He has to do more work in the second case. He has to spend his energy for providing both kinetic energy and potential energy. So that is part D. Now, next, come to question 6. Underline the correct alternative. Okay, just with the simple examples, we see the cases. When conservative force does positive work, force is conservative, it is doing positive work. Potential energy of the body, what happens to the potential energy of the body? For example, gravitational force is a conservative force. An object falls down. What happens? Object moves in the direction of gravitational force. Work done by gravitational force is positive, and it falls down. So what happens to potential energy? The potential energy decreases. Therefore, we can conclude when the conservative force does positive work, potential energy decreases. Now, case B. Work done by a body against friction always results a loss in friction. Work done by friction. When the object is in motion or impending motion, that time only you can see kinetic energy. Or sorry, that time only you can see friction. So motion or impending motion. So take the case of motion. It has kinetic energy. Due to friction, what happens to the kinetic energy? Gradually, the object getting stopped due to friction. So work done by friction reduces kinetic energy. Then next, the rate of change of total momentum of many particle system is proportional to, no doubt, proportional to external force. This is just a second law of motion. That's all. Then part D, in elastic collision of two bodies, the quantities which do not change after the collision, quantities remain conserved. That is the question, and you have studied already. It is total linear momentum and total energy. Next, come to question 7. State if each of the following statements true or false. Okay, with the reason. First one, in elastic collision of two bodies, the momentum and energy of each body is conserved. Each body is conserved. Answer is false. Why false? Elastic collision. You are studying elastic collision. Momentum and kinetic energy, total energy, etc. are conserved. But if you have two bodies, M1 and M2, they undergo collision, and after the collision again they continue to travel. Remember the case which you have studied. Here, what you have studied there, total energy, total initial energy is equal to total final energy, or total initial momentum is equal to total final momentum. But it is not the individual momentum or individual energy. The M1 may have a different momentum after collision. M1 may have a different kinetic energy after collision. But when you take the total momentum, that only conserves. Therefore, here the question says that each body. So, answer is false. Next, part B, the total energy of a system always conserved no matter when internal and external forces on the body are present. Here also. Okay, answer is false. Why false? Because it is mentioned about external forces. Suppose external force is there, which is doing positive work, just like we lift an object. When you lift an object using an external force, what happens? External force has done positive work, and the body will get an additional potential energy mgh. That means what happens? Its total energy increases. Okay. Therefore, we can say the total energy is not conserved when external force is doing positive work, because the energy of the body will increase. Okay. Therefore, the statement is false. Then part C, work done in the motion of a body over a closed loop is zero for every force in nature. Again, it is false. It is not applicable for every force. It is applicable only for conservative force. There are non-conservative forces like friction. For such forces, the work done over a closed path is not zero. Then next, part D. In an inelastic collision, the final kinetic energy is always less than the initial kinetic energy of the system. Okay, there you have proved that during an inelastic collision, kinetic energy decreases. Therefore, you can take this statement as true. But there are exceptions. Such exceptions you are not studying. Therefore, you need not go into that details. So, whatever you have studied in that level, according to the scope of your syllabus, you take the statement as true. Okay, now next question 8. Answer carefully with the reasons. Okay. In an elastic collision of two billiard balls, is the kinetic energy conserved during the short time of collision of the balls? Okay. So here also you have to see the wording there, during the short time of collision. That is what you have to see here. During the short time of collision. Look at here, two balls. Okay. Assume both the balls are having a perfect spherical shape. Now what happens? These two balls undergo an elastic collision. During the collision, what happens? During the collision, that small time of collision, there will be a small deformation in the spherical shape of the body. Here, that sphericality will be lost at the point of contact. That means the balls are pressed. If anything is pressed, just like a spring is compressed, like that, anything is pressed, then what happens? For a compressed spring, there is potential energy. The same manner, when the balls are pressed, there is a small change in shape. This change in shape means, it is elastic potential energy will appear there. That means momentarily what happens? This kinetic energy of the balls is partly converted, not the whole kinetic energy, but a part of kinetic energy is converted to potential energy. So far they are in contact. When they are out of contact, what happens? Again, this potential energy is converted into kinetic energy and they will continue to. So what is our answer? The answer is no. During the collision, again I tell you, during the collision, during the short time of collision, kinetic energy is not conserved. Kinetic energy is momentarily converted to potential energy. Afterwards, again, it is converted into kinetic energy. That is why total initial kinetic energy and total final kinetic energy are equal. But during the collision, due to the small deformation of the shape of the ball, momentarily their kinetic energy is converted to potential energy. So it is not conserved during the collision. Then come to part B. Is the total linear momentum conserved during the short time of elastic collision? Whatever the momentum is always conserved, because this kind of change in shape and all having no influence on momentum. Then what are the answers to A and B for an inelastic collision? Answer A will be same change, because in elastic collision also shape change will be there. Then momentum, in elastic collision also momentum is conserved. So in both the answers will be same. Okay, both the answers will be same. Then part D. If the potential energy of two billiard balls depends only on separation distance, potential energy depends only on distance between their centers. Is the collision elastic or inelastic? Okay. Potential energy depends only on distance. Potential energy, V, this formula you have studied. Sorry, not potential energy, V. Force F is equal to minus dV by dI or dx. You have studied this formula. In this case, potential energy depends only on distance. And this formula, what is this formula? This formula represents conservative force. So potential energy depends only on separation distance means the force is only conservative force. Potential energy depends on distance. So the force is conservative force. If the force is only conservative force, then the collision is elastic. Okay. Now, next question 9. A body is initially at rest, which u is equal to 0. It undergoes one-dimensional motion with a constant acceleration. Acceleration is constant. Power delivered to it at time t is proportional to. We can go for a simple solution. Okay, we start with the formula. Actually, you can use the methods of differentiation and all, but for you this is enough. V is equal to u plus 80. There u is equal to 0. Then, so you will get V is equal to 80. V is equal to 80. Now take the power formula. For P is equal to, power is the dot product of force and velocity you have studied. Then substitute there. Is equal to F into 80. Then again, it question says that acceleration is constant. Acceleration constant means force is also constant. Therefore, we can say power proportional to T. Power proportional to T. So option 2 is the correct answer. Now, next, come to question 10. A body is moving unidirectionally under the influence of a source of constant power. Question says that power is constant. Its displacement in time t proportional to displacement. Okay. So here again we have to start from the formula which we have used in the previous problem. V is equal to u plus 80. U is 0, so here also you have to take, it's not mentioned in that question, but you have to take u is equal to 0. It is just the continuation of the question 9 only. U is 0, so V is equal to 80. P is equal to F dot V, or we can substitute the value of V, so F dot 80. Now from there you will get P is equal to MA, F is equal to MA into 80. So A square will come there. From there you can find the value of A. A is equal to, what do you get? Under root P divided by M. Under root P divided by M. Now displacement equation, S is equal to ut plus half at square. This is equal to ut plus half at square. Again, u is 0 only. Substitute the value of a in that formula. Substitute the value of a, then p is constant, m is constant. So you will get s proportional to, you can just exclude the constant, you will get t square divided by t raised to 1 by 2. Simplify it, you will get s proportional to t raised to 3 by 2. This 1 by 2 you have to take the numerator, it becomes 2 minus 1 by 2. 2 minus 1 by 2 is 3 by 2. Okay, therefore option 3 is the correct answer. That's about the question 10. Now, question 11. Force is given there. Body is moving along z-axis and its displacement is 4 meter along z-axis. So what is the value of displacement? Displacement, you will get 4k cap. That meter is the displacement. And what is the work done? Which formula you have to use? W is equal to F dot S. So substitute the values of F and S. S is equal to 4k cap only along Z axis. Okay. So you will get the answer. 2. Next question 12. An electron and a proton are detected in a cosmic ray spin. Okay, the first with the kinetic energy 10 kilo electron volts. That means kinetic energy of electron. You can take it as Ke is equal to 10 kilo electron volt. And kinetic energy of proton, we can take it as Kp is equal to 100 electron volt. 100 kilo electron volt. Okay. 100 kilo electron volt. Then which is faster? That is the question. Now conversion formula, mass of electron is given here, mass of proton is given here, and the conversion formula between electron volt and joule is also there. But actually, as we are going to take a ratio, you need not go for making any conversion of energy there. Okay, just we calculate the ratio. Take the ratio Ke, kinetic energy of electron divided by kinetic energy of proton is equal to, what do you get? Half me v square, that is the kinetic energy of electron, divided by half mb vp square. The half will be cancelled. Cross multiply the equation. Then v by vp is equal to, v by vp is equal to under root mbke divided by MEK. Now both the masses are there, high energies are there, substitute the values and find the ratio. If the ratio is greater than 1, then electron has more velocity. If the ratio is less than 1, then proton has more velocity. Okay. Find the answer. Next question 30. Raindrop of radius 2 millimeter. Radius 2 millimeter. R is equal to 2 millimeter. You need to convert into meter. From height 500 meter, h 500 meter, falls with a decreasing acceleration until at half of its original height. It attains its maximum, that means terminal speed, and moves with the uniform speed thereafter. What is the work done by the gravitational force on the drop in the first and the second half of the journey? Okay, so first and total height we can take h. First half and second half means in each half it travels for a height h by 2. So how much is the work done in the first half? So W half is equal to mg h by 2. Mass is not given there. Instead of that, radius is given. How to find the mass? Mass you can find volume into density rho into g h by 2. Then again, radius is given. How can you find the volume? Volume is equal to, assuming to be spherical, 4 by 3 pi r cube rho g h by 2 will give the first answer. Work done. Work done by the gravitational force is equal to the decreasing potential energy. Okay. Now density is not given. Okay, density of water you have to take as 1000 kilogram per meter cube. Is the density of water. Now, next in the second half, what will be the answer in the second half? In the second half also, you can see in the second half again the same h by 2 height it travels. Therefore, the work done in second half also you will get the same answer. That also will be mg into h by 2. So, work done in first half and work done in second half will be equal. Now see the second part of that question. What is the work done by the resistive force on the entire journey if its speed on reaching the ground is 10 meter per second? Final velocity is given 10 meter per second v. And initial velocity we can take rest because it falls. Okay, therefore we can calculate the change in kinetic energy delta k. Change in kinetic energy is equal to final kinetic energy minus initial kinetic energy, and initial kinetic energy is 0. So directly you can calculate the value of m v square. V is 10 and m again you have to take a 4 by 3 pi r cube rho. Now we apply work energy theory. Work done by gravitational force delta Wg plus work done by resistive force, or just we take a work, that is enough. Okay, work done by gravitational force plus work done by resistive force is equal to change in kinetic energy. Work energy theorem we apply. Work done, total work is equal to change in kinetic energy. And Wg you will get when you add these two quantities, this 1 and 2, both are equal. You add them, you will get a total work done by gravitational force And delta K you have calculated already from here, half of V square. From there, work done by resistive force you can calculate. So you will get a delta K minus WG. Okay, the answers are small values, so carefully you have to do with the decimal points and all you need to consider. Then only you will get a proper answer in this question. Okay, now come to question 14. A molecule in a gas container hits a horizontal wall with a speed 200 meter per second at an angle 30° with normal and rebounds with the same speed. Is momentum conserved in the collision? Is collision is elastic or inelastic? It rebounds with the same speed means no change in kinetic energy. So first you can conclude in this process kinetic energy is conserved. Kinetic energy is conserved. Let's come to the moment. Okay, see what happens there. Take the case of a molecule. Its mass is very less. The mass of the molecule, maybe in the order of 10 power minus 10 or 10 power minus 50, like that. Very small mass. But take the case of wall. The mass of the wall is very high, extremely high compared to mass of the molecule. Okay, so we can say the mass of the molecule is much less than mass of the wall. In such a situation, what will happen there? Okay, you just consider the momentum of the molecule and the momentum of the wall. The mass of the molecule is very small, extremely small, so its velocity is observable. See the velocity of the molecule. Now, the mass of the wall is extremely large compared to that of molecule. Therefore, in this product, the velocity will be very small. Therefore, we can say that when the molecule hits the wall moves. Momentum is conserved. Molecule gives its momentum to the wall. The molecule is moving, velocity is observable, its mass is extremely small, and during the collision, the molecule gives its momentum to the wall so that wall moves. But when wall moves, what happens? Because of heavy mass, velocity of the wall is extremely small so that it is not observable. In such a situation, we can say momentum is conserved. The molecule gives its momentum to the wall moves, but you cannot observe that because of huge mass of the wall. So momentum is conserved in the process. First molecule hits the wall moves with the same momentum, molecule becomes rested. Then like that you can take, then the wall will come back, hits the molecule and the molecule bounces back. That is the actual process of that. So what we can say, momentum is also conserved. As momentum and kinetic energy are conserved, then we can say the collision is elastic in nature. The collision is elastic. Now, next question 50. Question 15. A pump on the ground floor of a building can pump water to fill a tank of volume 30 meter cube in 15 minutes. So quantities you have to see. Volume of the tank is given. Volume of the tank V is equal to 30 meter cube. Then time is given 15 minutes. That means 15 into 60 seconds. Then height h is given 40 meter. And efficiency of the pump is 30% efficiency. That means only 30% of energy is used to lift the water. How much electric power is used? Electric power PE we need to calculate. Electric power P. Now look at the formula carefully. So we can have a potential energy of what? Potential energy is equal to mgh. Potential energy is equal to mgh. Again, mass is equal to volume into density. Mass of volume density of water, you have to take 1000 kilogram per meter cube. Then gh is the potential energy. Now power is equal to energy by time. Here energy means potential energy. So V rho g h by time t. And then look at there. So you can calculate the power required to lift the water by substituting the values. You can find the answer. And this power, according to the question, this power is only the 30% of electrical energy spent. That means P is equal to 30% of electrical energy. 30% of electrical energy. And you have to find electrical power. Sorry, not energy, electric power we spent. Electric power is equal to, you will get 100p divided by 30 will give you the final answer. Next, question 16. Two identical ball bearings in contact to each other. That is shown here. Ball bearings 2 and 3. And they are at rest on a frictionless stem. Okay, then what happens? An identical ball bearing moving with the velocity v, that means the ball 1. Then you will get collision there, and 3 cases are given. And if the collision is elastic, question says that already the collision is elastic. Which of the following is a possible result? Okay. So first we can calculate initial kinetic energy. Ke is equal. Look at there, only one ball is in motion. We can take a mass of the ball is m. So velocity v. So kinetic energy is half m v square. Now take case 1. Final kinetic energy is equal to, you can see there, 2 balls are in motion with velocity v by 2. So 2 balls means mass you have to take 2m into velocity v square by 4. So you will get the answer 1 by 2 into half m v square. is equal to Ki by 2. So what does it mean? Kinetic energy becomes half there. So kinetic energy becomes half. Okay, let's see the other case also. Here, final kinetic energy Kf is equal to only one ball is in motion. Its mass is em, velocity is v, half m v square, which is equal to initial kinetic energy. And here, three balls are in motion. Af is equal to half into total mass is 3m, velocity is v square by 9 is equal to, you will get 1 by 3 into half m v square is equal to half m v square is again initial kinetic energy. Now a collision is elastic provided momentum is conserved and kinetic energy is also conserved. Okay, look at the kinetic energy. You can see the kinetic energy is conserved only in the second case. Therefore, that is the only possible result. The second case where kinetic energy is conserved. Initial kinetic energy is equal to final kinetic energy. Next, question 17. A bob, okay, you can see in the diagram also, bob A, 30°. It's bob B, both are having same mass. And bob B is at rest. So, this is the case, the collision of two particles of identical mass. One is in motion, while second one is at rest. This particular case you have studied in the theory. After collision, what will happen in this case? They will interchange their velocities. That means object A, which is moving, becomes rest, and object B moves with the velocity of A. So after collision, here A becomes rest and B moves with the velocity that of A. So that's a elastic collision. In such a situation, the question is how high does the bob A rises? Bob A will not rise because after collision, bob A becomes rest. So height h is equal to 0 only. Then next, the bob of a pendulum is released from a horizontal position. Okay, again pendulum. It's a pendulum. But the pendulum is in the horizontal position now, like this. From there, it is released. And length of the pendulum is 1.5 meter. That means this vertical height is 1.5 meter. What is the speed with which the bob arrives at the lowermost point, provided 5% of its initial energy is lost? So what is the velocity of the bob at the lowermost point? In horizontal position, you know its energy is only potential energy, mgh, and at the lowermost point, it has only kinetic energy, no potential energy, because lowermost point the height becomes 0. Here value of h is 1.5 meter. Now you can take total initial energy is potential energy is completely converted to kinetic energy at the lowermost point of mv square. because at the lowermost point only potential and only kinetic energy, at the horizontal position only potential energy. But at the same time, the question says that 5% of initial energy is lost against air resistance, which means 95%, remaining 95% of initial energy is converted to kinetic energy. So 95 by 100 into mgh is equal to half mv square. From there you can simplify the equation and you can find the value of. Now next, a trolley of mass 300 kg carrying a sandbag of 25 kg is moving with a speed at 27 km per hour on a horizontal track. After a while, sand starts leaking out of a hole on the floor of the trolley at a rate of 0.05 kg per second. Okay, what is the speed of the trolley? So you can take in this way, sandbag leaking, and the weight of the sandbag is acting downward and normal reaction is acting upward. They mutually cancel each other always. If it is full of sand or half of the sand is leaked, whatever weight acting downward is cancelled by the reaction upward. And you can see there when the trolley moves with the uniform velocity, that means there is no force in the horizontal direction. In horizontal direction, force is zero. No force in horizontal direction. So vertical direction, the force is cancelled, the reaction and weight. Horizontal direction, no force. If there is no force, what is the condition of a moving body? According to first law, it will continue with the same speed. So what is the answer? When the bag is empty, then also the trolley is moving with the same speed, 27 km per hour. It is moving with the 27, no change in speed as there is no force in the horizontal direction.